What if you ran the same product concept through two different development methods and compared what engineering actually received at the end? That's this case study. Here's the summary. We had the same product, but we did two trials. One method produced a solid feature list and a set of open questions for engineering to resolve. The other produced design inputs tied to specific users, ranked by severity, with failure modes identified before engineering ever opened a file. This table is the punchline of the case study, and the rest of this video is the proof. The product is actually a service product called Suncor 360. I created a product concept using fictional companies and products. This is a fictional use case of a residential solar installer. They have about 31,000 customers across 14 states, and their current Better Business Bureau rating is a B+. They've decided that they need to hit a strategic goal of an BBB rating of A+ by the end of the next year. So that's about a year and a half they have to do this. The Suncor 360 is actually a post-installation service redesign. They want to target 3 service tiers, but the core challenge here is that they're currently averaging 5.3 days to respond to a service request, and the premium tier promises 24 hours. That gap is not a technology problem, it's an operations problem. It involves multiple user types, homeowners, field technicians, prospects, at-risk customers, with competing priorities and real constraints. That's why it's a good test case. It's the kind of product where what you hand to engineering actually matters. So we ran 2 full concept development trials. We used the same product brief, the same green light packet, which is all the information that the company used to determine if this project was a go, if it's something they wanted to develop and pursue. We also used the same cross-functional team: engineering, manufacturing, quality, marketing, sales, and customer success. This team I developed as experts in their field and represented by AI agents. They communicated in a Slack-type interface and worked through different methods. Trial 1 used a traditional method. There were 5 structured rounds. There was kickoff, users and use environment, concept exploration, risk and feasibility, and finally a summary. Trial 2 used the methods and frameworks that are outlined in Pierce the Design Fog, including the ADEPT framework. Trial 2 used 6 ADEPT rounds. Each round runs the full align, discover, examine, prioritize, teamwork cycle, but applied to a specific lens: the concept space model for the use process, benefits, and symptoms. Then further exploration of benefits with a benefit impact, symptom impact for symptoms, and a value-added analysis to get more detailed information from the use process. Since I used AI to run both complete trials, it made it possible to compare the outputs directly. The AI is the mechanism that made this fast. The story is what came out. Let's start with the traditional method. There were 5 structured rounds, and the team did real work. I want to be fair about that before I show you what it hands to engineering. 5 engineering design inputs came out of 5 sessions. There was diagnostic fidelity thresholds, noise reduction algorithms ensuring that ticket validity was high before a technician was even dispatched. Bomb to SKU precision, diagnostic reports hard linked to the bill of materials. Every ticket arrives with a confirmed SKU list. A safety critical anchor, hard-coded logic protocols for high voltage and structural failure modes, determining earlier who needs to be sent and what's needed to solve the problem. System health scoring, a real-time metric that distinguishes environmental soiling from actual hardware degradation. And on-site verification. But engineering also received 4 open action items. Not answers, but questions. Is the 24-hour SLA achievable with current headcount? How do you restock parts depot for the top 20 failure modes in 48 hours? How do you sell prevention to a customer who feels fine right now? And there are 27 open Better Business Bureau complaints that have to be resolved before launch. Now, here's what's worth noticing about the design inputs themselves. They're feature described. Diagnostic fidelity thresholds, bomb to SKU precision, those are system capability names, not user needs or benefits or symptoms. There's no traceability to a specific user or a specific step in how the service actually gets delivered. There's no prioritization. Which of these 5 matters most is left for engineering to figure out, and there's no analysis of what goes wrong if an input isn't met. Engineering can build from this, but they're carrying ambiguity that wasn't resolved in concept development. Now, the same product, same team, using the Pierce the Design Fog and ADEPT frameworks. 6 rounds of analyses, each running the full align, discover, examine, prioritize teamwork cycle applied to a specific lens. This method works from the user's experience forward, not from the feature list backward. It takes more rigor, but here's what came out of it. The team mapped the full 9-step service resolution use process, from anomaly detection to closed-loop confirmation, and then analyzed each step for what adds customer value, what's business required, and what adds nothing. 2 highest leverage steps emerged: the remote diagnostic gate, which is the automated analysis that determines whether a truck roll is actually needed, and the inventory handshake, which verifies parts are in stock before a technician is dispatched. One insight the traditional method never surfaced: the 24-hour SLA clock starts at customer notification, not at anomaly detection. That gap in the process is a design input. Engineering needs to know it exists before they build. The team applied benefit impact and Kano analysis. They mapped each benefit to what the user actually experiences, then rated it. What's basic are table stakes. If you don't meet this or you fail to meet this, it destroys trust and ruins reputation. For performance measures, they're really a linear return. The better you do it, the happier customers are. And attractive measures are the differentiator. They are what separate you from your competitors and the other people providing similar services. The critical finding is that the 24-hour SLA is basic. Engineering needs to protect it, but it's not a marketing hook. Meeting it doesn't win customers, it just prevents losing them. What is a differentiator? Proof of prevention. Showing the homeowner what didn't break, the anomaly that was caught before they noticed anything wrong. That's what distinguishes Luminos from other competitors in the field. And that design insight came from working forward from the user's experience, not from the feature list. They also ran symptom impact analysis, essentially FMEA thinking at the concept stage. For each potential failure, the team identified what goes wrong, rated its severity on a 1 to 6 scale, and derived the specific design input required to prevent it. 2 severity 5 failures: silent failure, which is a false negative at the diagnostic gate, where the customer's system is underperforming but nobody knows. And the other one is radio silence. The human fallback is delayed during the 24-hour window, and the customer hears nothing. There are 2 severity 4 failures: a first visit failure, where stale inventory data sends a technician without the right parts, and a broken warranty promise in rural zones where the SLA extension was never disclosed. Each one has a specific design input: manual override, protocols, heartbeat monitor triggers, real-time inventory API, geographic zone logic. Engineering isn't guessing what matters, they're building to it. Let's put them side by side across the 5 dimensions that matter. Design inputs. With our traditional method, we got 5 items that are feature described. Using Pierce the Design Fog, we have a use process map, Kano-rated benefits, and a severity-ranked symptom analysis with a required design input for each failure mode. Not a longer list, a richer one with structure. Traceability. Our traditional method had inputs named as system capabilities. With Pierce the Design Fog, every input was traced to a specific user, a specific step in the use process, and a specific failure consequence. Prioritization. There were 5 inputs with an equal weight. With Pierce the Design Fog methods, the Kano category plus the symptom severity tells engineering what to protect first. Severity 5 items are protected before severity 4. Basic requirements are kept basic, not oversold as differentiators. Failure mode visibility. Using traditional concept development, we got a project-level risk register, 4 risks and high level. With Pierce the Design Fog, we have design input level symptom analysis. The failure mode style thinking happened in concept development, not in engineering. Finally, open items. With our traditional methods, we had 4 broad action items, unassigned. With Pierce the Design Fog, we have 3 specific questions, each with a named functional owner. Engineering owns the inventory staleness tolerance definition. Operations owns the SLA pause rules for rule zones. UX owns the resolution artifact architecture. Here's the clearest way to show what changed. Both methods produce the same answer, a real-time inventory API. But look at what engineering receives. On the left, a feature name, real-time inventory API. That's it. On the right, the same feature with context. If the inventory handshake provides stale data, the technician arrives without parts. First visit failure, severity 4. Design input, real-time inventory API with staleness tolerance defined. Same answer, one has context, one doesn't. Engineering building to the right-hand version knows what they're protecting against, what failure looks like, and what done means. Engineering building to the left has to figure all of that out on their own time. Before we close, notice what the comparison example didn't show. The inventory API was one case where both methods landed on a similar answer, expressed at 2 different levels of specificity. 3 of Pierce the Design Fog's design inputs don't appear anywhere in what the traditional method handed to engineering. Those failure modes were never surfaced, not described less clearly, not presented at all. Engineering would have found them eventually, in engineering where the cost of discovery is much higher. The fog didn't disappear, it got cleared in concept development, where it's cheap, instead of in engineering where it's expensive, or instead of later in the product development process where it's harder to make changes. It's defined early as an input when those engineering decisions are being made. If your team's concept development process is handing engineering a feature list and a set of open questions, this is what changes when you use a structured method that works from the user's experience forward. Suncor 360 is just one case. I'm running the same experiment on other product concepts, and I'll link to those in the description as they publish. The method is in Pierce the Design Fog. If you want to put it to work with your team, workshop and advisory information is in the description. Thanks for joining me on this case study. This has been a production of Dini Enterprises.